In this final video for Module 4, we're going to look at a heat exchanger and a turbine. Now, a heat exchanger, I said, could be analyzed a couple of different ways. I am going to take the point of view of doing this all as a single unit, so both fluids at once, multiple streams. In this case, I have a steady state heat exchanger. It's designed to take in cool air and circulate it over tubes that contain steam. The air will then be heated and the steam will leave the exchanger at a lower temperature than it entered. So steam is going to enter this exchanger at 200 kilopascals, 200 degrees C. Air is going to enter at 35 degrees C. I want the air to leave at 45 degrees C. My job here is, if I'm going to have a flow rate of air of 50 kilograms per minute, how much steam do I need in this exchanger if the steam exits at 200 kilopascals with a quality of 75%? So it's a saturated liquid vapor mixture when it leaves. Okay, so translate that given information. It's helpful to separate these out by the fluid streams. So I have one line for the steam, the inlet and exit temperature and pressure, or pressure and quality. But remember, two pieces define the state, so this is enough to well define the inlet and the exit states. For air, I have a flow rate, 50 kilograms per minute, and I have an inlet temperature and an exit temperature. I do not have pressures, qualities, anything like that. So this one, I only have one item defined, and so in order to analyze this, I'm going to need to make an assumption. I'm going to assume that this is an ideal gas. Now, my first law. I have this expression here. So the heat transfer, when I consider both fluids at once, I assume that the exchanger is well insulated and all heat goes from one fluid into the other and nothing leaves the system. There are no moving parts, so work will be zero. I also am, because of the wording of the problem, plus this is very standard, I will assume that kinetic and potential energy are negligible or zero. So I'm left with the sum of the enthalpies out equals the sum of the enthalpies times the flow rates in. Okay? But I have two different materials, two different ways of calculating the enthalpy. So my simplified form of the energy balance is just going to be the sums of the exits of M times H equals the sum of the inlets times M sum of M times H. Wow, that was a tongue twister for me. So I need data. Well, for the steam, that's not that big a deal. I can look in the steam tables and I find this. It's pretty easy to find. For the air, I can use air tables, or I can use, since this is a small change in temperature, 10 degrees is not very much, I can assume that C sub P is approximately constant. And if you wanted to verify this, if you look at C sub P as a function of temperature, the change is in the fifth digit. It would round to 1.005 and 1.006, I believe it was. But really, this is very close to being a constant C sub P. So I'm going to use constant C sub P times delta T to approximate the enthalpy change of the air, and I'll use actual enthalpy data for the steam. So if I plug those numbers in, I end up with this. Now I have the mass flow rate of the steam is the same for its inlet and exit, and so if I take this and rearrange solving for M, I end up with the mass flow rate of steam of 0.7 kilograms per minute. Now that may feel very surprising to you that 50 kilograms per minute can be heated with only 0.7 kilograms per minute of steam. But it's because the steam carries so much more energy with it. And it's still losing the same amount of energy or enthalpy over the course of the problem, but it's a denser way of carrying it. So let's look at a turbine. Now in this turbine, we're going to also use process efficiencies. Start introducing those in a little bit better. In this case, I've got steam expanding in an adiabatic, so again, Q is 0, steady state turbine from 1,000 kilopascals and 280 degrees C, so a really high pressure and temperature, to a temperature of 200 degrees C. And what I want to know is what's the actual exit pressure if the turbine's 85% efficient. And then also we'll do an entropy calculation here. Okay, so I'm going to need to get the data. I have enough information for the inlet, so 1,000 kilopascals, 280 degrees C. Now, from the tables that I provided, you're going to have to interpolate to get that one. The pressure is given, but temperatures, I think, are 250 and 300. So, but you can interpolate and pause the tape and go check that and make sure you interpolate and get those values. So I found the H and I found the S because they asked for the delta H. And then I have my exit. I'm asked to find the actual exit if the turbine is 85% efficient. Now, here's where it gets a little bit tricky, because what I have to do on a problem like this when they give me a process efficiency is figure out what the ideal exit would be. And ideally, this is going to be reversible and adiabatic. Reversible and adiabatic means it's at constant entropy. So the entropy from the inlet helps me define the exit state if it's ideal. So I have a temperature and I have the entropy. And I can then go through the tables and find an H of 2855. Now again, this is going to require some interpolation. So you're going to have to work a little harder on this problem than you have on others. So I have those. Now let's use the definition of the process efficiency for a turbine. It says that the enthalpy change of the actual turbine divided by the entropy change of the ideal enthalpy change of the ideal turbine is going to be this process efficiency of 0.85. Now the ideal I can calculate. It's the inlet minus the exit, assuming that the delta S is 0. Okay, so I have those. The actual enthalpy change is going to be the inlet minus whatever the exit really is. But if I know the process efficiency, that's my only unknown. So I can solve this for the exit enthalpy. I get 2878. Okay, so what good does this do me? Well, I know it's 200 degrees with this enthalpy. And so I can go to the tables and I can interpolate, or in this case it turns out I chose numbers so that it worked out. It was in the book. It's roughly 50 kilopascals, and the entropy is 8.158 kilojoules per kilogram Kelvin. So I have the actual exit pressure, I have the actual exit entropy, and so delta S is 1.112 kilojoules per kilogram Kelvin. So that concludes our examples for this lesson. In the next module, we're going to be putting these together to build a power plant, so using multiple ones of these simple processes in combination to build a cycle.